stress max divided by 2. And for this case, stress max can be also equal to stress x divided by 2. Okay, so this is the one condition. Okay. The next condition we have is when we have a case where this is our element now. And for this case, we have a normal stress X. Okay. We have a compression, or we have zero stress Y. Okay. So but we have shearing stress. Okay. So we have our shear XY is equal to shear YX. Okay. And then from here, this is our X, this is our point Y, and this is our point Z. Now, this stress state, if you were to look, have you seen this stress state before? Most of the time, under any sort of combined axial load, bending, and shear and torsion, we usually have this sort of what? Stress element distribution, yes or no? Right? If you look at the examples that we did, if we look at the example that we did in week 11, okay, look at this. Can you see that? Do you know why I'm so excited, or you have not a clue? You think I'm crazy? Okay, you think I'm crazy. Can you see this stress state, right? This element has one normal stress, has one shear stress, and the rest of the stresses are equal to what? 0, yes or no? So what I did just now is I randomly go to an example. Okay, so this example over here, I wonder what it is. Is combined loading, yes or no? But if you look at the element, look at the stress state of the element. It also has what? One normal stress and one shear stress, and the rest is equal to what? 0. Can you see that? Right? Then it happened. If we were to look at the example that we did today, right? We did this example last Friday. It happened to be the what? The same, where you have one normal stress and you have what? One normal stress component and one shearing stress what? Component, yes or no? So i.e., what am I flipping about is you have one of this and you have one of this, right? If you go to what I've written down, you also just have one of this and just one of this. Can you see that? Okay, that is the common part. So for this case, right? So I will put down here that this is the most common loaded element. So if we were to sketch, move circle now. So you have normal stress, and then you have your shearing stresses, right? So this will be your normal stress, shearing stress, element rotate clockwise, element rotate anti-clockwise. So this is your point X, this is your point Y, and over here, this is your point what? Point Z. So from here, we can sketch our mole circle. We've done this a lot of times. 2, 4, 5. Okay. So this is one of your mole circle. Right? And we know that this belongs to your what? Plane. And the XY plane is the in-plane one. Okay. You have the other two circles. So the other two circles we have is one circle is over here. And then the other circle 6, 8. This is the other circle. Okay. So the other two circles, which is your out of plane. Okay, so this circle, which is your out of plane, this belongs to your exact plane. And over here, this belongs to your YZ plane. So when this is the case, what we have is over here, this is your stress mean. And over here, this is your what? Stress max. Okay. So we can calculate where tau max. So for this case, we can determine that tau max is equal to stress max minus a, when I say stress max, all right, stress mean. Stress max minus by stress mean divided by 2. Okay. Now, so to calculate our stress max and stress mean, we know the center of circle. All right, center of circle, which is our stress average. And this will be equal to our stress X plus by stress Y divided by 2. And then the next thing that we want to calculate is our radius of the circle. Which correspond to our tau max. So this will be equal to square root of stress X plus by stress Y over 2 squared plus by shear XY squared, like what we had before. Okay. So we know that stress max and stress mean will be equal to stress average plus or minus by what? Tau max. Okay. So when that's the case, what we have is tau max. So we're going to substitute everything into equation 1. We will have tau max, like what we have before, is equal to stress average plus by tau max minus by stress average minus by tau max. And then the whole thing divided by what? Divided by 2. So over here, you will have 2 tau max over 2, which is also equal to your tau max. Okay. So you can directly use this expression over here, right? Tau max is equal to stress X plus by stress Y over 2 squared plus by shear XY squared. If and only if, right, your mole circle look like this. When I say look like this, is when you're what? And when your XY plane are your in plane. Now the third case that we will see, that's where you have to be careful. And this is, I wouldn't say not common. I've seen it throughout my engineering practice. I've seen it once or twice only, okay, but it's not common. So it's a case where you have a situation where you have your structure now. So we still have our, like what we had before. If I will copy the stress state that we had before, we have stress X. And then you have your shear XY. which is equal to shear Yx. The component with is your stress Z down here. Okay. And this is not common. Okay. I'm not saying it's impossible, but it's usually for submerged or operating structures that are not in atmospheric pressure. I.e., this thing can submerge in what? Water, or an airplane going up, okay, where the cabin is what? Pressurized. Are we clear? So this is the third scenario. So when it is in this situation, we have to be very, very what? Cautious. What do I mean by cautious? So if this is my X, this is our Y, okay, this is our Y, and over here, this is our Z, okay? So you have to be cautious now because of this, okay? So this is our element now. No, this is our Mohs circle. Okay. So we know that this is our normal stress, shearing stress, okay, clockwise, anti-clockwise. So we can have our normal stress over here. So now this is our stress X. This over here is our stress Y. And then we have a shear. Right? So like before, this is our point X. This is our point Y. Okay. However, we have a Z. Okay. So the Z, stress Z is in compression for this case. Okay. So this is our stress Z. So point Z, because stress Z got zero normal stress, this is our point Z. So now when we start to construct Mohs circle, so this circle over here is for our what? XY plane. So this is where we have our what? In plane. Okay. And then we have the other circle. Okay. So this is our next circle. So this circle belongs to our XY plane. No, XYZ plane. And then we have our last circle over here, 2, 4, 6, 8, 10, 12, 6. We have our last circle over here, 6, 2. Does it look circle or no? Wow, it looks very circle, Eugene. So this is our what? Third circle. So now you realize that over here, this is our what? Stress max. And now over here, this is our what? Stress mean. So at this case, we have to be careful. So we know, I'm almost done, okay? Bear with me. We know that stress max is equal to stress average plus by tau max. Now, tau max over here belongs to the XY plane. Okay, tau max XY plane. Okay, I put tau max over here. And we know that stress mean is equal to what? Stress Z. Okay. So when we compute our tau max, will be equal to stress max minus by stress mean divided by 2, the entire expression changed. So that's why we have to be careful. So stress max will be equal to what? So stress average will be equal to stress X plus by stress Y divided by 2 plus by the square root of stress X plus by stress Y divided by 2 squared plus by shear XY squared. And then after that, minus by stress Z, and then the whole thing divided by what? Divided by 2, right? As I say, this scenario is not very common, okay? That's why fundamentally we have to check, okay? So if your circle appear this way, you cannot, when your circle appear this way, you cannot use the expression what? You cannot assume that this expression tau max can be used to determine your what? The diameter of your shaft or to compute the stresses. Are we clear? Okay. I'll see you guys in an hour's time.